Alright, so given this matrix here, we can go ahead and decompose it into its components, which would be the ones, and then we got the twos, and then we have the threes here in the end, which are along the diagonal. And so USP, a uniquely solvable puzzle, would be one in which you can swap any number of rows in each of the different components, and when you merge them back together to create a matrix, that none of the entries overlap, right? And so this one here would not be uniquely solvable because we can see that the ones stay the same. The twos, oh, I'm sorry, the ones, let's see. Okay, so the ones would stay the same, that's right. The twos can be placed on the diagonal by swapping these two guys. So we get a 2 here, and we get a 2 here. And then we could swap these two guys, which would give me a 2 here and a 2 here. So then, yeah, so we put the 2's on the diagonal, and then we could put the 3's swapped around by putting this one here, which would swap that row up 1 and this row down, so we get the 3's down here. And then we would swap these two rows, so then we would get this 3 up here, this 3 down here, and the result would be, whoa, and we would get 2, 2, 2, and then we would get, what is it, 3, 3, 3. So we would get this matrix as a result of doing the row swaps, and then when we merge them back together, there is no overlap, right? So let's see, what do we get? We get 1, 3, 2, 1, 2, 3, and then 2, 1, 3. So because there is no overlap after we've swapped a row, at least one row, it's not USP, right? It's only USP if we are not able to create a non-overlapping matrix after making one row swap, at least one row swap. So that's my understanding.